The college started postgraduate courses in the year 2008 in chemistry and social work. After becoming autonomous, it added few more courses in all disciplines. Today, the college has 11 postgraduate programs under choice-based credit system pattern. The courses are designed to give weightage in core papers to learn more of skills, supported by soft core papers and open elective from other departments to enhance students' knowledge beyond their program. The University of Mysore has recognized the chemistry, social work, journalism, and physics departments as research centers. 4 students have enrolled for their PhD program. To provide better facilities, an independent postgraduate center was established with well-designed labs, library, classrooms, and multimedia projectors with internet connectivity and uninterrupted power backup. The overall program outcome of postgraduate courses is to train the students to acquire knowledge leading to innovations, entrepreneurship, new technologies backed by effective communication skills. The curriculum of the programs is regularly revised as per the need of the society. Some of the major innovations introduced in the curriculum are open electives, interdisciplinary papers, and Swayam MOOC courses. The students are trained through blended teaching with flipped classes. The students and faculty members continue to enrich their knowledge by organizing and attending seminars, workshops in the college. To inculcate research culture among the staff and students, the department...
A pleasant morning to everyone. I welcome you all to Day 6 of the Science Academies 6-day online lecture workshop organized by the Department of Physics, sponsored by the Science Academies of India in association with St. Philomena's College, Autonomous, Mysore. Kindly be with us till the end of the program as we will be sharing a feedback link to you. On completion of that feedback form, you will receive an e-certificate. Today we have with us Professor G. Umesh to present his lecture before you. I welcome him to the program and over to you, sir.
Thank you, ma'am. Good morning, friends. Yeah. Good morning to all of you. So in the past 2 days, we have been looking at how to measure different parameters of materials. In particular, our focus is on metals and semiconductors. And as I was telling you yesterday, it is very important to measure as many different physical properties of a material as we can, simply because we want to use these materials in different applications. And for a proper and efficient use of these materials, it is very important to be able to measure the physical parameters and then design the device or the electronics for the application which we have in our mind. So in the same spirit, today we will look at the measurement of mobility first, and then we will also look at the techniques for measurement of band gap of semiconductors. Okay. So I will first describe to you 2 methods for measurement of mobility. And then I will tell you about measurement of band gap. Okay. Let's look at the working principle for the measurement of mobility. We already have formed some idea of a solid. I would like to again emphasize that making to solve a certain problem in science or while trying to tackle a problem in your research, you need to adopt a certain model. Okay, and in material science, often we deal with materials, so we need to first be clear about the model which we will adopt to learn about the material. So the model that we have adopted for solids is that of a gas of free charge carriers sloshing around in a solid. Sloshing means moving around in a solid freely like a gas within the boundaries of the material. And apart from the charge carrier gas or gas of charge free charge carriers, you also have big heavy ions at the lattice points. Okay. Today we will see that we may have to add one more feature to this model, and we will probably come across that when we deal with the measurement of band gap. All right. So we have seen that mobility of charge carriers is an important parameter to measure in semiconductor. We define mobility of any charge carrier, whether it is metal or semiconductor, the definition is same. We define it as the magnitude of the drift velocity when you apply a unit electric field. Or in other words, you apply an electric field across a sample, okay, and the electric field should be 1 volt per meter. That is what the meaning of unit electric field. Okay. In that case, if we are able to measure the drift velocity, remember drift velocity is a constant, has a constant value. It is dictated by the collisions in the medium, and therefore it is constant. And it turns out that the drift velocity is expressed in units of meter square per volt. Okay. We have seen in our previous lectures that the different materials have this property of electrical conductivity, and we have seen that the electrical conductivity, one of the expressions for electrical conductivity sigma is that it is equal to n times q times mu. We were dealing mostly with electrons, so we were putting q equal to E earlier. Okay. In this expression, n is the density of charge carriers, free charge carriers. Okay. And mu is the so-called mobility. Okay. We know that the value of Q is 1.6 10 to the power of minus 19 coulombs. This is the electronic charge. So if we measure the electrical conductivity, about which we learnt yesterday, okay, if we measure electrical conductivity, and if we somehow are able to measure N, the carrier density, then one can compute the mobility. So this is the basic principle which we will use. So a measurement of electrical conductivity of semiconductor, okay, so gives us a product N times mu, okay, and then because Q is known, Q is simply 1.6 10 to minus 19. In a second measurement, if we determine N, then from the value of N mu, we can then evaluate the value of mu. Okay. But in the experiments, we need to keep in mind that the value of N in a semiconductor is going to be a strong function of temperature. Okay, you raise the temperature, the number of free carriers goes up. It goes up quite sharply. Okay, so when we make a measurement, we must keep the sample at a constant temperature, so that so in measuring the electrical conductivity, we need to take that care. Now, it the experimental process for determining the carrier density is the measurement of Hall coefficient or the Hall effect experiment. Many of you may have already done this experiment, and it is, let me tell you that characterizing a semiconductor in terms of its carrier density by the measurement of Hall coefficient is a very standard method. It is adopted in the industry also, okay, to characterize the material that that are prepared in the industry for making devices. So it's a very, very widely used technique, and it is good to know that know how to do this experiment with some desired accuracy. Okay. Let's look at briefly look at the working principle of Hall effect. You may already know about this. Hall effect is something which in which the force on a charge carrier moving in a magnetic field, a moving charge moving in the presence of a magnetic field, we know experiences the Lorentz force. The expression for Lorentz force is Q into V cross V. Okay, so we exploit this physical phenomenon of Lorentz force acting on moving charges, and this is how we measure the what is called as Hall voltage. So to understand this phenomenon, let us look at a semiconductor crystal in the form of a slab. This is seen in the diagram. The slab has a width W and a length L, and it has a small thickness T. T may be of the order of a millimeter or half a millimeter. Okay, whereas L and W can be of the order of 5 millimeters. So this is a very thin slice of semiconductor with perfectly parallel faces. Okay, and what we do is, as seen in the figure, the coordinate. Look at the coordinate system. The edge, which is called length L, is parallel to the x-axis. The edge, which we call as width W, is parallel to the z-axis, and y-axis is normal to the surface of the crystal. Okay, so what we do is we imagine that a current I flows from flows along the positive x-axis from one face of the crystal to the other. We will see how to do that in the experiment. And the crystal, the semiconducting crystal is also subject to a magnetic field in the y direction. Okay, as shown. Magnetic field is shown as B, and the current, conventional current, is shown as I. Okay, so I is along positive x-axis, B is along positive y-axis. Okay, so now let us analyze what happens to the carriers. The carriers, let us say, look at holes which have positive charge. Whatever I say about positive charge would hold for the electron, except that the sign of the charge is negative. So if we imagine the positive charges to be moving along the positive x-axis, that will be represented by the current I, which is shown. Okay, and then there is a magnetic field in the y-axis. So moving charges have a velocity in the positive x-axis, and B is along positive y-axis. So V cross B. Okay, if you use the right-hand rule, V cross B, which is a measure of the force. Okay, force per unit charge actually, that is in the positive z direction. Okay, so while the when the charges are moving along, they will experience this force due to the applied magnetic field B. We assume that B is not only constant, but it is also uniform all across the sample, and therefore all the electrons which are drifting along the positive x-axis with a constant velocity will experience a force along the acting along the positive z-axis, and these positive charges will tend to move in the direction of the electric field, in the direction of the force, and therefore the positive charges will accumulate at the edge of the crystal, which is perpendicular to the positive z-axis. Of course, there are two edges. One is in the front and one is at the rear. If you look at the figure, okay. So if positive charges accumulate at the front edge, equivalently, negative charges will seem to accumulate at the opposite end. And therefore, what happens is this will create an electric field. Okay. And the electric field is directed in the minus z direction. Okay. Because of this charge accumulation, then the accumulation occurs because of the Lorentz force. You have a charge separation and a positive charge in the front edge of the crystal and a negative equivalent negative charge of equal magnitude on the opposite edge. Okay. And because of these this charge accumulation and the effective electric field due to the charge separation acting in the minus z direction, okay, from positive to the negative side of the crystal. Okay. Now this electric field will obviously tend to prevent the holes from drifting towards the front edge of the crystal. Okay. So there is a competition between the V cross B force due to the applied magnetic field and the force exerted by the field generated by the charge separation. And in steady state, the two will balance. Okay. When you balance the forces, it turns out that the balance will happen when the equation given at the bottom is satisfied. Okay. We see that V cross B, see, Lorentz force due to magnetic field is Q into V cross B. So if I take Q equal to 1, or if I calculate the force per unit charge, which is called as the electric field, I'll get E equal to VB. Okay, so that's why we have written E equal to VB equal to, and we put it equal to VH by the width of the sample. This is because, you see, the electric field is acting between the two edges separated by the distance W. Okay, and therefore this electric field can be expressed in terms of voltage as voltage per distance. So that is why VH upon W. Okay, so we could also say that a voltage is generated between the two edges which have the charge positive and negative charges. Okay, so this VH is called the Hall voltage. All right. So now let us see. We can estimate the current that is flowing. See, current is calculated, the formula is shown in the equation, I equal to NQV into WT. This NQV you will recognize is J. Okay. NQV is the definition for current density J. And W times T, if you see the previous figure, W times T will give the surface area of the edge into which the current is entering. Okay. So that is why the current is J times area. J is NQV and area is W into T. Okay. So you can see this easily from the geometry of the figure. So once I have this formula for I, and we also have the previous equation where VH would be equal to VB into W. Okay. So these two equations can be combined and you can show that VH is equal to BI by NQT, and which I can write as 1 by NQT is RH. Okay. We will write, okay. We will define 1 by NQT as RH, and therefore VH is written as RH into VI. So RH is defined as 1 upon NQT. This quantity RH is called the Hall resistance. So we have Hall voltage and Hall resistance. And we see that the Hall voltage, VH, is directly proportional to the magnetic field B, it is directly proportional to the total current I, and it is inversely proportional to the thickness of the crystal. Okay, the thickness of the crystal. All right, and the crystal has much larger values for W and L, but T is quite small. Okay, so 1 by T will be quite large. It also turns out that the voltage as measured by the voltmeter could be positive or negative. Okay, and depending on the sign of the voltage VH, we will get an idea of what is the charge. So, for instance, if N is negative charge, then VH will be negative. Okay, if N is positive charge, VH is positive. Okay, so when we measure VH, if the instrument shows a negative Hall voltage, that indicates an electron as the charge carrier. The instrument indicates a positive Hall voltage, it represents, then we are looking at holes. Okay. Another interesting thing is that for metals, N is of the order of 10 to the power of 28 or 27 meter per meter cube. This we have been talking about many times before. So 1 by N will be a very small number. Okay. So even if I have reasonably large current like 1 milliampere and a magnetic field which is about 1,000 Gauss, it is mentioned as 0.1 Tesla, and you know that 1 Tesla is 10,000 Gauss. Okay, so 0.1 Tesla would be about 1,000 Gauss, which is a fairly strong magnetic field. And if thickness is about 1 millimeter, it turns out that for metals, the Hall voltage is 1 nanovolt, very small. So unless you have a very sensitive nanovolt meter, you may not be able to measure that. That is why in our BSc or MSc laboratories, we often do Hall effect experiments using a semiconductor, not a metal. Okay. For semiconductors, the carrier density is much smaller by a factor of 1,000,000, and therefore it turns out that the Hall voltage is up by a factor of 10 to the power of 6, and it could be of the order of 1 millivolt. Okay, so this gives you an idea of what is the Hall voltage in semiconductors and metals. Measurement of Hall coefficient and the electrical conductivity will enable us to calculate the mobility as we had discussed earlier. Again, let us note that the electrical conductivity is given as is equal to N times Q times mu. We know RH is 1 upon N QT. Okay, so we can connect mu and sigma and RH from these two formulae. So we see that mu is sigma times RH into T. Okay, so we know the sample thickness. We can measure sigma and RH by separate experiments. And if we do that, we can compute the value of the mobility. Okay, so we have already learned how to measure sigma. So let's quickly look at how to measure RH. Hall effect apparatus is available in many MSc laboratories. So what we are going to use is going to be very similar to that. So it can be measured, Hall effect can be measured in the DC mode or the AC mode. Okay. By that, what we mean is that in the experiment, we employ a constant current flowing through the sample and a DC magnetic field. Okay. This method, or the DC method, is suitable when the mobility of charge carriers is high. Okay, in all semiconductors in which the mobility is significant. AC method is used, and the AC method, the change is that the magnetic field, applied magnetic field, is an AC magnetic field. Okay, the current through the device is always DC. The AC magnetic field which is applied can be AC. If the mobility is low, then the second method is suitable for measuring mobilities in materials with in which the mobility is low. So typically, when we say high mobility, it is something like 1000 centimeters square per volt second. And low mobility means about 100 times less, something like 10 centimeters square per volt second. Okay. All right. Now, if you look at the apparatus, typically, what we have, we should have a magnet, then we should have a semiconductor sample, and then we should have a constant current source to drive a current through the sample. And we must have a millivolt meter or a microvolt meter to measure the voltage. Okay, these are the three essential items. Usually, an electromagnet is used to create the magnetic field, and typically the electromagnet may have two different coils, okay, or two pairs of coils. Depending on the direction in which we want the magnetic field, one can switch either of these coils. We use a digital Gauss meter to measure the magnetic field generated by the electromagnet. And the electromagnet has pole pieces meaning the core is made of soft iron. So those are called the poles, and the cross section of the poles are called the pole pieces, or rather the gap between the two cores on the on two coils. Okay, you see, you should have a north pole and a south pole for the electromagnet. So therefore, there will be two poles. One pole is north and the other pole is south. The gap in between is where the magnetic field is created, and we measure the magnetic field in that gap. Typically, we keep the gap about a couple of centimeters to do the experiment. In such arrangements, it is normal to generate a magnetic field of about a Tesla. If we take greater care, then one can make an electromagnet which can go up to 2 Tesla also. Our measurements require up to a kilogauss, that is 1000 Gauss or 0.1 Tesla. So commercial electromagnets can be used in making these measurements. As I said, the semiconductor sample is taken in the form of a very thin plate. The width and length of the plate can be 5 millimeters by 5 millimeters. It can be a square piece, and the thickness may be a millimeter or half a millimeter. Well, this sample has 4 edges, thin edges, and therefore we make wire contacts with all the 4 edges of the sample. Okay, opposite contacts are used for driving the current, and so there are 2 pairs which are opposite in orientation. So 2 of the contacts are used for driving a current along one of the edges, parallel to one of the edges, and the other 2 contacts are used for measuring the voltage, okay, measuring the Hall voltage. This sample can be mounted on a plastic strip, just for conveniently positioning it between or handling the sample. Okay, because the sample is so thin, and if we are not careful, we can end up breaking the sample. Instead of that, it is mounted on a piece of maybe plastic, so that handling the sample would be easier. Okay. First thing is to calibrate the magnet. Calibration of magnet means to generate the graph which is shown below. We should know at what current does the magnet generate a certain field. So magnetic field B along the y-axis is plotted against the current supplied to the electromagnet coil. Okay. And by setting the current at different values and using a Gauss meter, one can measure the magnetic field and therefore plot this graph. Okay. This graph shows 2 curves. It shows 2 curves because 2 pairs of electromagnet coils are probably used in this instrument, and both of them are almost identical. Therefore, they generate almost the same magnetic field at a given current. Okay, this is just for you know getting the calibration graph is some kind of a fit to the experimental points, and the use of both the coils of the electromagnet gives us a better estimate of the average field at a certain current. Okay, so once we fit this graph to a linear equation, we see that the magnetic field can be computed by the equation which is shown here, B equal to 173 plus 2230.2 times the current I. So for a given current in the experiment, I can use this formula, which is obtained from the calibration graph, to calculate the magnetic field. Okay, right. Now, some details about how the experiment is done. The sample is, as I said, clamped onto a plastic holder, and this sample has to be placed between the pole pieces, and it is placed such that the face of the sample is parallel to the pole pieces. You see, the magnetic field lines are perpendicular to the pole pieces, and therefore, if we place the sample in this orientation, the magnetic field will be perpendicular to the sample surface. Okay, so essentially, knowing the direction of the magnetic field, which we would know from whether the which pole piece is north and which is south, we would know which is the direction of the magnetic field, and therefore we place the sample such that the magnetic field goes through the sample normally on its surface. I also said that there are four edges, thin edges of the square sample, and we have wire connections to all the edges. Okay. We drive a current through two opposite wire contacts. Okay, and then we measure the magnetic field across the other two contacts. Okay, so notice that the current flow and the orientation of the electric field would be perpendicular to each other, and that is how the measurement connections are made. Okay, typically a current of 0.5 milliamperes is made to flow through the sample, half a milliampere, and the microvoltmeter, okay, is used to measure the DC voltage across the other two edges. Okay. Now we vary the current on the electromagnet from something like 0.01 ampere to about 0.36 amperes in steps of something like 50 milliamperes. Okay, and keep recording the readings of the voltmeter at different currents. Once I know the current, one can compute the magnetic field for each current value which is set, and then we will have measured the Hall voltage. So therefore, we can plot the graphs. Okay, this graph shows Hall voltage as a function of the magnetic field, applied magnetic field, for different values of the current flowing through the sample, DC current flowing through the sample. Okay, so the DC current flowing through the sample is shown in the figure as starting from 0.5 milliampere all the way till 4 milliampere. Okay, in steps of 0.5 milliampere. The magnetic field is varied from about 200 Gauss to about 1,000 Gauss. Okay, I hope you have followed the basic principles in the measurement process. Okay, so once I do this, I can calculate the slope of each of these straight line graphs. We see that the Hall voltage is proportional to the magnetic field, as we had discussed earlier. We can calculate the slope for each of the graph. Okay, so we will get different slopes for different graphs, which means I get different slope values for different currents which are made to flow through the sample. So once I have this data from this graph, I plot the another graph of the slope calculated in the previous graph as a function of the current flowing through the sample. Okay. Once I do this, if we take the slope of the graph which you are now seeing, see, this graph is itself a plot of slope versus current. The previous graph was Hall voltage versus magnetic field. Using this graph, we generate data for plotting the graph shown now, slope versus current in the sample. Okay. Once I do this, I can determine the slope of this graph, which you are seeing, slope of, the plot of alpha, the slope alpha versus current in the sample, and the slope itself. Suppose the slope is beta, you can show that RH, the Hall resistance, is beta times T. You can check this from the expressions. So this is how we determine Hall resistance RH. Now we know that from the previous data is actually a measured data, and then that data yielded a value of beta to be something like 1.354 10 to minus 3 volt per Gauss ampere. And using this value, RH computed as beta times T, okay, we know T, the thickness of the crystal, it turns out to be something like 0.00675 meter cube per coulomb. From a separate measurement, you can estimate, or rather, from this, we get the number density of hole, because we see that RH is 1 by inversely proportional to the number density. So using the value of RH and the thickness, we can get NH. It turns out that NH is something like 9.26 into 10 to the power of 20 per meter cube. Okay. So once I know NH, then I can, of course, determine the value for the mobility. A similar data is also shown for N-type germanium. What we saw earlier was for a P-type semiconductor. Okay. This is for P-type germanium. So is this. And what we show here is for N-type germanium. Notice that the slope is negative in the case of N-type germanium, whereas the slope of alpha versus current is negative. Whereas in the case of P-type semiconductor, the graph of slope alpha versus current has a positive slope. This indicates directly the nature of the carrier. Positive slope would correspond to P-type, would correspond to a semiconductor which is P-type or dominated by holes. Okay. And a negative slope would indicate an N-type semiconductor. Okay. So from the slope of the graph, we can get the value of the carrier density and therefore the mobility as well. We can also therefore compute the mobility. In samples which have low mobility, okay, the conduction will be through both electrons and holes, and therefore they will be the expression for Hall coefficient can be shown to be as given in this formula below, and this is seen to be quite small. Okay, and Hall effect does not give charge density accurately in the case of low mobility samples. So for low mobility samples, as I said, the other technique of using an AC magnetic field is a better method. But we will stop here for this presentation. Okay, we'll take a break and come back to talk about the determination of band gap.
The college started postgraduate courses in the year 2008 in chemistry and social work. After becoming autonomous, it added few more courses in all disciplines. Today, the college has 11 postgraduate programs under choice-based credit system pattern. The courses are designed to give weightage in core papers to learn more of skills, supported by soft core papers and open elective from other departments to enhance students' knowledge beyond their program. The University of Mysore has recognized the chemistry, social work, journalism, and physics departments as research centers. 4 students have enrolled for their PhD program. To provide better facilities, an independent postgraduate center was established with well-designed labs, library, classrooms, and multimedia projectors with internet connectivity and uninterrupted power backup. The overall program outcome of postgraduate courses is to train the students to acquire knowledge leading to innovations, entrepreneurship, new technologies backed by effective communication skills. The curriculum of the programs is regularly revised as per the need of the society. Some of the major innovations introduced in the curriculum are open electives, interdisciplinary papers, and Swayam MOOC courses. The students are trained through blended teaching with flipped classes. The multidisciplinary peer-reviewed research journal with ISSN number to publish their research articles. The faculty members have completed UGC-funded research projects. The management also supports with seed money to carry out research. The college started postgraduate courses in the year 2008 in chemistry and social work.
Okay, friends. So we are in the last leg of our program. This is the last lecture, and what we are going to talk about is measurement of band gaps in semiconductors. In the previous lecture, I described to you techniques for measuring Hall mobility. I hope you were able to grasp what I was trying to tell you. So for measurement of band gap in semiconductors is a very important activity, because if you want to use a semiconductor for whatever application, you must have a idea of what is the band gap. Okay. For example, if you want to make a diode, laser, LED, light emitting diode using a semiconductor, you need to know the band gap so that you get to know what is the wavelength of the light emitted. Okay. Similarly, you can use the same semiconductor but with a different band gap as a photo detector. Okay. So this will give you an idea that you have to properly make the semiconductor for a particular application. If you are making an ordinary diode, you need to have a semiconductor with particular characteristics. If you want to make a photo LED, you have to use a semiconductor with a different set of characteristics. Okay, all right. We define band gap, as you all know, as the energy gap between the top of the valence band and the bottom of the conduction band. It may sound silly if I make the remark that sometimes we think of band gap as a distance. It's not distance. Okay, I've often come across students in MSc classes who think that band gap is a distance measured in centimeters. It's not that. It is a difference in energy. Okay, that is why we need to emphasize that it is the difference in energy between the bottom of the conduction band and the top of the valence band. Typically for semiconductors, it's of the order of an electron volt, or in large band gap semiconductors, it may go up to even 2 to 3 electron volts. Okay. For many electronic devices, we use silicon and germanium, which have band gap of the order of 1 electron volt. We can measure band gap by several techniques. One is by measuring the resistivity of the sample. We will discuss how to do that in this lecture. The second is by measuring the reverse saturation current and the temperature dependence of the reverse saturation current using the semiconductor in the form of a PN diode. Why we use a PN diode will be made clear when we discuss that. And the third method, which is often employed in the laboratories, including research laboratories, is optical absorption measurements. Okay, so we will briefly discuss each of these techniques, and it is quite possible that many of you may already be using these techniques for measurements in your either research labs or the PG labs. Simplest method for measuring resistivity of a semiconductor is what is called as the 4-probe technique. Again, many MSc labs have equipment which are called 4-probe measurement apparatus. This is a technique which is essentially measurement of current voltage characteristics of the sample. Okay. The method employs 4 probes. These probes are thin wires, either of copper or gold, and you bring these wires in contact vertically on the surface at 4 different points. They are put into simple mechanical contacts. One may use a little bit of silver paste to make the electrical connectivity better. Okay, and it is something like the wire standing on the surface of a sample which is taken in the form of a plate of a similar size as in the previous experiment. See, we discussed the Hall effect experiment, or the Hall voltage measurement. So the sample crystal of semiconductor would be of the almost the same dimensions, and the wire probes which we are going to use in 4 probe method have to come into contact on the surface and point and are oriented vertically on the surface. Okay. Secondly, all these probes are lined up along a straight line. It may be parallel to one of the thin edges of the sample. Why is it in the straight line will become clear shortly. So when we put 4 probes on a straight line, we see that 2 probes are on the outer side, and the other 2 probes will be between the outer 2 probes. So we'll call the outer wires as outer probes, and the 2 inner 2 wires within this outer probes as the inner probes. See, the outer probes will be called as current probes for discussion, and also we push a current into the sample through the current probes or the outer probes, and we measure the voltage across the 2 probes which are the so-called inner probes, and we will call them as the voltage probes. So what happens here is, when you drive a current through the sample using the outer probes or the current probes, near the point where the probe comes into contact with the semiconductor, the local electric field would not be uniform, because the contact is a point contact. The electric field vectors will be oriented in all possible directions, and the electric field will, if we imagine the electric field to be created inside the semiconductor due to the applied bias voltage, then the electric field will start from the positive probe and end up into the negative probe inside the semiconductor. So you can imagine the lines, field lines, electric current field lines inside the semiconductor, and the field lines start from a point at the positive probe. Okay. When did it get interrupted?
No, just
Okay.
10 seconds.
All right. So what there was a, sorry for the brief interruption. There was some internet problem. What I was telling you was that the using the current probes or the outer wire contacts, we push a current into the steady, constant current into the sample, and we measure the voltage across the 2 inner probes, which are within the 2 outer current probes, and the inner probes are called voltage probes. And the reason for this is, as I said, that when we drive the current flows because of an electric field in the semiconductor. Electric field is created by the voltage difference between the positive current terminal current probe and the negative current probe. Okay, and this electric field is not uniform, and say electric field vectors are not straight lines close to the point of contact of the current probes. But in between, as the electric field lines start from the positive current probe and terminate at the negative current probe, the distortion in the electric field is only near the contact points, but in between there's a region, small region, where the electric field is uniform and parallel to each other. So that is the region in which the voltage probes pick up the voltage. Now, because we are driving a certain definite current into I mean, you know how to express resistivity in terms of the measured resistance and the geometry of the sample, so we can evaluate the resistivity. Okay. Now it turns out that the resistivity is a function of temperature, and therefore the resistance is also a function of temperature. It varies as shown in equation 1. Resistance as a function of temperature is proportional to some t to the power of nu, a certain parameter, depending on the material, times exponential Eg by 2 kT. This is a standard expression which you will find in books on solid state physics. This factor t to the power of nu is a result of the temperature dependence of mobility of the charge carriers. In the previous lecture, we discussed how to calculate the mobility. Okay, and it is seen that the mobility would also be dependent on temperature. Why? Because you see, the collision frequency or the scattering probability will depend on the number of charge carriers, which in turn depend upon the temperature. Okay, so the temperature dependence of mobility is quite strong. It turns out that in materials which we normally use, value of nu is of the order of 1.5. So you can put nu equal to 1.5. We take the logarithm on both sides, we get equation 2, log of r. We're taking natural logarithm. So that will be some constant plus 1.5 times log of t, which gives the log of t to the power of nu. And then log of exponential is simply the exponent. So you see, you know how to get equation 2. What we do is we plot a graph of log of r minus 1.5 log t. Okay, this factor is, as you see from equation 2, is equal to a plus Eg by 2 kT. So we plot this factor against 1 by t.
Sorry, sir. Small internet fluctuation.
Okay, no?
Yes, sir.
Okay. Once again, a small interruption. Sorry about that. So one can calculate the band gap Eg, and in the previous formula, you have Boltzmann constant in the denominator. You can express it in terms of electron volt per degree Kelvin, and therefore get Eg straight away in electron volts. So Boltzmann constant you can put as 88.6 10 to minus 6 eV per degree Kelvin, and or put it as 88.6 micro electron volts, and then you can get Eg micro electron volts. Okay. So in this experiment, as I said,
excuse me, sir. Sir, we are unable to see the. You have not shared the screen, sir.
Sorry, sir.
No problem. But this is blocking the. Okay, once again, some internet problem. So as I mentioned earlier, for this experiment, what we require is a constant current source capable of supplying current of about up to 10 milliamperes and a millivoltmeter to measure the hall voltage. The voltage across the inner probes. Okay, not hall voltage. Yeah, I'm getting mixed up. As I said, for the 4 probes, to get a good electrical contact with the sample, because we just push the wire probes till it hits the surface. Okay, hits in the sense just comes into contact. So it's a mechanical contact. Such contacts are not very good electrical contacts, and therefore to make it a better contact, we can use a silver paste, which is a conducting paste. Okay, so then the probes will be in good electrical contact with the sample. That is the reason. The sample is something like 10 millimeter by 5 millimeter by about 1 millimeter thickness or 0.5 millimeter thickness. Okay. We may also do the experiment by varying the temperature. Okay. To do that, what we do is that we mount the semiconductor sample on an aluminum block, taking care to electrically insulate the sample from the aluminum block, because aluminum block is also metal and we don't want a shorting of the circuit. Okay. So this can be easily done. And the temperature of the aluminum block has to be monitored. So a platinum resistance thermometer or a copper constant thermocouple is attached to the block for temperature measurement. This is a standard procedure, so I will not discuss the details of the thermocouple. What we will simply note is that we can measure the temperature of the aluminum block using the temperature indicator. Okay. No, this is not moving. All right. So in the experiment, the current through the current probes is varied in the range 1 to 10 milliamperes. And the voltage across the voltage leads is measured and recorded. And the experiment is done over a range of temperature from room temperature to about 100 degrees centigrade or something like 300 to 400 degree Kelvin. And as I said before, from the data, we evaluate values of log R minus 1.5 log T, and then plot this along the y-axis versus 1 by T on the x-axis. So ln R minus 1.5 ln T on the y-axis, 1 by T on the x-axis. And then we see that the graph is a straight line. We can calculate the slope of the graph. And for the sample for which the data is presented, the slope is something like 5967 plus minus some 11. Okay. And EG, as we noted earlier, can be calculated knowing the slope, and its value turns out to be about 1.02 plus minus 0.01 electron volt for silicon. As you all know, for silicon, the band gap is something like 1.1. And so this is quite close to the value. Okay. Another method for measuring the band gap is by employing a PN diode. See, this experiment is interesting because PN diodes are very cheap devices, low-cost devices, and they are generally available in the market, open market. And in this experiment, actually, you can use one of these commercial PN diodes, or you can use several PN diodes and then determine the average band gap. Okay. What we exploit here is the temperature dependence of the reverse saturation current in the PN diode. Okay. And by measuring that, one can get the band gap. So what we do is that we use a PN diode both in the forward bias as well as in the reverse bias. Why do we use do the measurement in forward bias? This will be clear if you look at equation 4. This is the equation for current, diode current versus the bias voltage. And this is well known, and you use this equation many times in your teaching or classroom. So in the above equation, V is supposed to be positive for forward bias, or if V is positive, we call it forward bias. If V is negative, we call it reverse bias. And this factor eta, which appears in the equation, is what is called as the non-ideality factor. In the ideal case, it is something like its value is 2. And for practical cases, like the diodes which we buy in the open market, value of eta turns out to be less than 2, maybe in the range 1.7 to 1.9 or thereabout. So what we do is we first evaluate the value of eta by experiment, and then use the value of eta, and then do the measurement in the reverse bias. Okay, and look at the variation of the reverse saturation current as a function of temperature. Formula 5 shows the variation of reverse saturation current with temperature. Again, this expression is fairly well known, and if you want the background on how to get this, you can look at books on solid state physics. In this expression, there is a parameter m, and typically the parameter takes values between 1.5 and 3. And we will see the use of this parameter. From the experiment on forward bias, we already know eta, and therefore, knowing eta, we use this equation to evaluate the value of Eg, the band gap. So, at room temperature, which is something like at about 20 degrees, which is a little lower than room temperature, which is about 313 degree Kelvin. The value of kT, you know, Boltzmann constant, so you can calculate kT, is about 27.7 milli-electron volt. And typically, if we use a voltage of 1 volt, then EV by kT becomes more than 36, which is a big factor. So exponential EV by eta kT is much greater than 1 in the forward bias case. So in the forward bias case, the equation for the current is as shown by equation 6. Now, one can take the natural log of both sides, and you get equation 7. And so what we do is we measure the forward current as a function of the bias voltage. Okay, and then we plot log of forward current versus the voltage. So if you look at equation 7, please note that the reverse saturation current is almost a constant, is practically a constant, and therefore this is an equation which resembles the equation for a straight line. So if we plot log of I forward versus V, we get a straight line. Okay, and from the slope of the straight line is given by the coefficient of V in equation 7. So it is E by kT into 1 by eta. Okay, since I know the temperature, we do this experiment at room temperature. So I know the value of T, I can evaluate eta. because we have, from the graph, we have determined alpha. Okay. It turns out that, so here is the graph of the forward current versus voltage. It's a straight line, and when the slope for the experiment done on the diode used in this experiment is 1N4148, which is a standard diode which you can get in the market. And at 300 Kelvin, the slope value is something like 20.6. And therefore, from the slope, we can get eta. In the second experiment, we have to measure the reverse saturation current. So we bias the diode in the reverse sense. We apply a constant voltage greater than 1 volt so that the diode is driven into reverse saturation. So a constant reverse saturation current flows through the sample. Okay. This current, reverse saturation current, is seen to be a function of temperature. Okay. And so we measure the reverse saturation current as a function of the bias voltage at different values of T, and then plot ln of reverse current plus m times log ln of T, and plot this as a function of 1 by T. We again get a straight line as in the previous case. Okay. And the slope of the straight line is, if you see the expressions, it is given by beta equal to minus Eg by eta k. So since from the first experiment we have determined eta and k is Boltzmann's constant, b is the slope of the new graph that we have generated. Therefore, Eg can be evaluated. So here is a graph of log I reverse plus m log t versus 1 by t, and it's a straight line. We see that the slope is something like minus 7,000, and one can determine the band gap. Okay, so I have another 15 minutes, so I will just quickly read what I have written here. We can use an inexpensive and widely available PN diode available in the market. One example is 1N4148. And we measure the forward bias. In the measurements on forward bias is done at room temperature. The forward bias voltage can be varied from 0.3 volt to about 0.55 or 0.6 volts in steps of 50 millivolt. You see, in forward bias, always the bias voltage is within 1 volt. Okay. The diode is in series with a 2K resistor, so that when the current flows through this, the resistor is in series with the diode. So the same current flows through this resistor, and one can pick up the voltage across the resistor to estimate the current. So we have the value of the current, and we know the bias voltage, and therefore the experiment can be done, as we discussed earlier. From the data, it turns out that for the diode 1N4148, which was used, eta has a value in between 1.8 to 1.9. In the case of reverse bias experiment, we use a standard battery, you see, torch battery, 1.5 volt battery, and this is applied to the diode, and the diode is in series with a 470K resistor. Okay, so again, the voltage is measured across the 470K resistor to estimate the current, reverse saturation current, and the sample is placed inside a furnace because we have to vary the temperature, keep raising the temperature. The furnace is designed so that we can increase the temperature in the furnace at a very slow rate by properly adjusting the current of current in the furnace. Okay, so the rate of temperature increase is maintained at around 1 degree per minute for in the experiment. The voltage across the 470K resistor is recorded for every 10-degree rise in temperature. And the range of temperatures is from room temperature to about 130 to 150 degrees centigrade. And using this data, we plot natural log of bias voltage minus 3 times natural log of the temperature against 1 by T. And we again get a straight line. It is shown in the next slide, but from the slope of the straight line, which is something like minus 7,000, the value of eta was found to be 1.82, and the band gap came to about 1.14 electron volt. Okay, so this is about 3% higher than the standard value for silicon. Finally, I will quickly tell you the principle used in measurement of band gap by absorption measurements in the semiconductor. Okay. Any material is characterized by a refractive index, and the refractive index can be a complex quantity. The imaginary part of the refractive index is a measure of the absorption in the sample. Okay, and the real part is what contributes to the speed of the wave in the medium. Okay, it's the real part is what we call as the refractive index in the normal discussion, and K is connected to the absorption coefficient. So if we assume this as the expression for the refractive index, we see that if a wave is propagating in the semiconductor medium, the electric field of the wave is what is given by equation 11. Okay, it's a expression for a plane wave, and we see that the expression on the right side is E naught exponential minus omega kappa upon C into Z times exponential I omega t minus n by C Z. Okay, that exponential I omega times t minus n by C Z will take care of the propagation of the wave. Exponential minus omega kappa by C into Z will indicates the exponential damping of the electric field due to absorption. Okay, so this is the factor which shows that the light which propagates through the medium slowly dies out, or its amplitude exponentially drops. If the amplitude drops, then the intensity also will reduce, and intensity is square of the amplitude, electric field times the E times E star, and if we calculate that, we get an expression shown in equation 11. Okay, this is a standard expression which you would have seen earlier also. I intensity of light along the direction of propagation, which is the z-axis, is equal to I naught, which is the initial intensity, times exponential minus alpha z, which indicates an exponential decay of the intensity. Here alpha is the absorption coefficient, and it is linked to the kappa which occurs in equation 10. Okay, it is 2 times omega by C into kappa. Now there are different mechanisms by which absorption occurs in the semiconductor, and in this context, as I said, we will introduce a new aspect to the model of the semiconductor which we had discussed in the very first lecture. The model being that you have in the crystal, semiconductor crystal, the ions form the lattice background, the carriers form the electron carrier gas. For instance, n-type semiconductor will have an electron gas which is freely moving within the confines of the solid sample. To this, we add this concept of a plasma frequency. So what we say is that this electron gas in the crystal and together with the positive ion lattice forms a solid state plasma. What is a plasma? A plasma is a collection of positive and negative charges which are quasi-neutral, which are almost electrically neutral. And one characteristic of this kind of plasma is that the electrons oscillate with a certain resonance frequency given by the plasma, so-called plasma frequency omega p. And one can show that the magnitude of the plasma frequency is given by equation 13, 4 pi Ne square by m star times epsilon core, where epsilon core is the refractive index of the material. Otherwise, you would have seen this formula for normal plasmas as expressed as omega p. I think it should be omega p square. Omega p square is 4 pi Ne square by m. Okay. So please take it as omega p square equal to 4 pi Ne square by m. Omega p itself is square root of the right hand side. What is the importance of plasma frequency? One consequence is that a wave, electromagnetic wave, with a frequency greater than the plasma frequency will not be able to propagate in the medium. Only waves with light with frequency greater than the plasma frequency will penetrate into the semiconductor sample. This is the behavior of a plasma medium. Okay. So now, n the free carrier density and m star is the effective mass of the carrier in the as shown, which occurs in equation 13. And this plasma frequency is usually small in comparison with the light that we might use in the experiments. The IR, we may use IR, visible or UV frequencies. In every case, it turns out that omega is, the frequency of light is much greater than the plasma frequency for the semiconductor sample. So in such a case, kappa, due to these free carriers, okay, is given by equation 14. So what it means is, while the plasma oscillations are set up because of random collisions and of the carriers, energy is absorbed simply because of the plasma behavior of the carriers. And that absorption is given by kappa free, which is shown in equation 14. Notice that this kappa free varies inversely as the relaxation time. 1 by relaxation time is the collision frequency. Therefore, kappa free is proportional to the collision frequency, which could be electron-electron collision or electron-ion collision. Okay. And it is inversely proportional to omega square also. So from 12, we see that the absorption coefficient, one can, knowing kappa, you can calculate alpha by the formula which we saw earlier. And we see that the absorption coefficient due to free carriers varies as inversely with the frequency of the light wave. Okay. Usually in semiconductors, this value of alpha free is pretty small, and many times it may or may not be very important. Okay. However, we note that if the temperature changes, suppose the temperature increases, then the carrier concentration will increase, and this will result in the absorption coefficient increasing with temperature, because absorption coefficient is given in terms of omega p square, which depends on the carrier frequency. Okay. Apart from this, there is a second contribution to the absorption in semiconductors, which arises because the photons which are interacting with the semiconductor may excite an electron from the valence band to the conduction band. And we very well know that this will happen if the energy of the photon is greater than the band gap. Okay. So this is usually well known to you, because we say that photons are absorbed in the semiconductor if the energy of the photon is greater than the band gap. Okay. One matter of detail in this, all this is that in the interaction, both energy and momentum have to be conserved. Okay. And therefore, the matching of wave vectors of the photon and the electron electron, essentially, which means the free carriers, this has to be looked into. Okay. Typically, wave vector of a photon is of order 10 to the power of 6 per meter. Wave vector is 2 pi by lambda, therefore the units are 1 upon meter. While the dimensions of the Brillouin zone is of the order of 10 to the power of 10 per meter. Okay. So the importance of Brillouin zone is that the wave vector of the free carriers would be of the order of 10 to the power of 10 per meter then, which is much larger than the wave vector of the photon. Okay. So it turns out that in momentum balance, which is essentially balancing h cross k initially and after the interaction, okay, h cross is of course a constant, and you see k for the free carriers does not change much because k of photon, which is involved, is very small. So for conservation of momentum, the wave vector of the electron, which is excited from the valence band to the conduction band, okay, is practically the same. All right. Now in semiconductors, we have two varieties of semiconductors. One is direct band gap semiconductor and the other is indirect band gap semiconductor. So since I'm running out of time, I have just 2 minutes. I'll quickly show you the result for direct band gap semiconductor. Okay. What we do is we propagate light through the medium and then measure the absorption of the light. Okay. We see that the light is absorbed only beyond a certain frequency. Okay. Now, frequency omega can be expressed in terms of energy by multiplying it by h cross. So one can talk about a threshold energy, photon energy, which corresponds to the frequency beyond which the light is absorbed. Okay. So the threshold energy can be measured in direct band gap semiconductor like indium antimonide or gallium arsenide. And the graph is seen to be as shown in the diagram here. Okay. So absorption coefficient versus the photon energy, which means the experiment is done over a range of wavelengths of light, indicates is seen to be as shown here. And the point where it touches the x-axis gives us the estimate of the band gap. Okay. So this is a very simple concept. And we can also plot square of the absorption coefficient as a function of photon energy, which gives us a straight line. And for a lead sulfide sample, this straight line intercepts the photon energy at around, this is between 0.4 and 0.45 electron volt. And that is the band gap of the sample. So I will stop here because we have almost exhausted our time. And if there are any questions, please post it. We will then give you the answers through correspondence or email. Okay. Thank you very much.
Thank you, sir.
A very good afternoon to all our participants and dignitaries on the dais. There's a Chinese proverb which goes like this: learning is a treasure which accompanies its owner everywhere. Yes, learning is a continuous process. Not everyone can pass a pool of knowledge. There are special ones who can do this full on. And we have two such special personalities with us who have expanded our horizon of knowledge in this 6-day online lecture workshop. The lecture sessions included topics like reciprocal lattice, Brillouin zones, periodic potentials, which gave us a deep insight to understand concepts like band theory of solids, thermoelectric power and its applications, semiconductors, their types, Hall effect, mobility of charge carriers, etc. were few of the topics that were taken up during the online lecture workshop. Overall, this 6-day online national lecture workshop has helped all of us gain more knowledge and taken our understanding of concepts to the next level. Now that we have come to the end of a 6-day online lecture workshop titled Energy Bands in Solids and Electrical Transport Properties of Metals and Semiconductors, organized by the Department of Physics and sponsored by the Indian Academies of Sciences in association with St. Philomena's College Autonomous, Mysore, we are here to formally conclude it. I now request Professor Shobana Thomas, Coordinator, Head, UG Department of Physics in Philomena's College, Mysore, to welcome our beloved guests and participants.
A very good afternoon to everybody, dignitaries present in the studio, and all the participants who have logged in and have stayed with us for these 6 days. It is with immense joy and satisfaction I stand before you to welcome you all to this valedictory function. I would like to welcome the president of this function, Reverend Father Maria Xavier, Vice Rector of St. Philomena's Institution. A warm welcome to you, Father. Usually, the Science Academy's lecture workshop is conducted for 3 days with 12 lectures. But when we had to adopt to the webinar mode, we had to change the way we conduct the workshop. We were not able to do more than 2 lectures per day. As a result, we had to extend the workshop for 6 days, and we had our apprehension that the participants may not log in for 6 days. But it is with joy I want to announce that almost all the participants have joined us on all these 6 days and stayed with us. And it is with pride I can say one of the reasons is the choice of our resource persons, especially Professor R. Srinivasan, retired Director, UGC DAE Consortium for Scientific Research Indore. Professor is very closely associated with our institution, and today he has agreed to be the chief guest of this valedictory function. I take this opportunity to welcome Sir. A warm welcome to you, sir. I welcome Professor Odbert Pinto, Director, PG Studies and Research Center of this institution, who has guided us in conducting this webinar. A warm welcome to you, sir. I welcome our resource person, Professor G. Umesh, retired Professor of Physics, NITK Surathkal, who has delivered 6 valuable lectures. A warm welcome to you, sir. I take this opportunity to welcome our mentor and guide, Professor D. Revanasiddhya, Head of the Department of PG Physics, St. Philomena's College. A warm welcome to you, sir. Warm welcome to all the members of Physics and Journalism Department who helped us to conduct this webinar. Last but not the least, a warm welcome to all the enthusiastic participants who have stayed with us all these 6 days, and I hope you will extend the same support when we conduct webinars or lecture workshop in the future. I want to make this announcement. The Department of Physics is again organizing an international lecture workshop in the webinar form on supernova and neutrinos, sponsored by Indian Academy of Sciences during 21st to 24th February 2021. I repeat, International Webinar Lecture Workshop on Supernova and Neutrinos from 21st to 24th February 2021. Request you all to join for the webinar and extend the same support to us. Thank you all and a welcome to all of you.
Thank you, madam. I heartily extend a warm welcome to you. Few of the participants of the 6-day online lecture workshop have come forward voluntarily to express their opinion regarding the program. I now request the participants who will be providing their feedback to turn on their camera and to unmute their
very interesting and useful for physics enthusiasts like us. I'm quite grateful for having been able to hear such great physicists and professors like R. Srinivasan and G. Umesh. Thank you so much, sir.
Good afternoon, everyone. Myself, Sujay Shekhar, pursuing PhD in the University of Mysore. It was an immense pleasure to attend this online lecture workshop focused on energy bands and electrical transport properties. Starting from day 1 to day 6, all the lectures were incredibly insightful and helped me in enhancing my knowledge and deepen my understanding. The best part of this lecture was the speakers have delivered the concepts from the basics and elevated those topics for higher understandings, which has helped, I think, all kind of audiences. I heartily thank the speakers, Professor R. Srinivasan sir and Professor G. Umesh sir, for taking an keen interest in delivering the lectures and providing study materials also, which help all the participants for future references. The study material is not only well equipped with the concepts, but also with exercise problems. I'm sure the students will get the understanding and insights of the concepts while working with these kind of problems. Being a former student of St. Philomena's College, I have seen the institution has continuously organized many conferences each year. So to make sure the students have up-to-date knowledge in the multidisciplinary fields. And this year is no exception. I heartily thank the organizing committee of St. Philomena's College for conducting unique, skill-developing online workshops, even in this kind of stressful pandemic situation, which will surely increase the learning enthusiasm in students. The idea of airing the webinar not only in Zoom but also in YouTube platform is also, I think, it reached many audiences. I'm sure the workshop has helped all the students and faculty. I thank Reverend Father Leslie Moraes, Dr. Bernard Prakash, Ruth Shantikumari Madam, Professor Pinto sir, Professor Srinivasan sir, showing his medal, and Shobana Thomas Madam, and my Professor Reverend Sidaya sir for giving me an opportunity to express myself. Thank you, everyone.
Thank you, Mr. Sujay, for your valuable feedback. I request Ms. Vanshika, if she is there, to provide her opinion.
Yes, ma'am, I'm there. Good afternoon. My name is Vanchika Singhania. I'm a student of Modi University. I would like to say that this 6-day workshop has been a very wonderful opportunity for all students to explore their horizons in the area of electronics. And as a student of bachelor's having electronics in my ongoing semester, it has been very fruitful for me to enhance my knowledge in it and know about it a bit more. The notes that are provided are also very informative and will definitely help me during my masters. Such programs are very helpful for physics enthusiasts like us. I'm quite grateful for having been able to hear such great physicists and professors like R. Srinivasan and G. Umesh. Thank you so much, sir.
Thank you, Ms. Vanshika, for your feedback. Thank you, dear participants, for your valuable feedback. I request Professor R. Srinivasan to deliver the valedictory address.
Members of the days and participants. This was the first time that I conducted an online course, and I didn't know whether people will be present for all the 6 days of the course. Because usually people are very enthusiastic on the first day. If it is a contact course, we can certainly see how many people are there in the hall. But because there is not a contact source, people have an opportunity to bunk. But I was very happy to hear that a majority of the participants continued with this online course for all the 6 lectures. I was told that out of nearly 150 participants, 50% were teachers and 50% were students. And it is my hope that this course benefited not only the student participants, but also the teachers in learning something new which they did not. I don't know how many of the teacher participants knew about cyclotron resonance technique for measuring effective mass or precise optical absorption techniques for measuring the band gap. I hope you got some knowledge about these 2 techniques from this course. I would like to thank the faculty of the physics department of St. PHILOMENA'S College and the people who are involved in organizing and seeing that this online course went off without a hitch. I am very thankful to all of them, and I am thankful to all the participants. I have given you my email address. Any participant is welcome to contact me if he has any doubt or he would like to express an opinion on the course. Thank you.
Thank you, dear Professor, for your precious time that you are spending with us, and your untiring enthusiasm keeps us all motivated. Due to some technical issue, Dr. Padma Prasad Karthikeyan missed out giving us feedback. I now request Dr. Padma Prasad Karthikeyan to share his opinion with us.
Namaskar, sir. So good morning to all. So it is my pleasure to provide the feedback on behalf of the participants. I think all the participants will agree in saying that we had a wonderful CMP treat, condensed matter physics treat by Professor Srinivasan sir and Umesh sir during the past 6 days. I would like to call them as Pitamahas of condensed matter physics. That means grandfathers of physics. So thanks to wonderful lectures. It is a pleasant journey in the ocean of condensed matter physics. So, with the permission of Srinivasan sir and Umesh sir, I want to share my experience in terms of condensed matter physics terms, like similar to the X-ray diffraction, which is useful to identify the structure of the solid. The sound waves of Srinivasan sir is able to understand what is the image what we are able to create on condensed matter physics on our brain. And another thing is, like Umesh sir has talked about phonons. So actually, he has created a huge vibrations on the individual cells of every human being. So I don't know whether it is right or not. I would like to say that like phonons, we can say the quantization of the vibration what we are getting as cellons. That means quantized cell vibrations. Okay, so so thank you for your nice lecture, sir. And also, I would like to thank the organizing team members who has contributed a lot in making the function a grand success. Thank you, one and all. Thank you, sir.
Thank you, sir. I now request Reverend Father Maria Xavier, Vice Rector, St. Philomena's College Autonomous, Mysore, to make the presidential remark.
Respected dignitaries on the dais, and dear participants, those who are participating on this webinar from past 6 days, my dear friends. In every religion, the main focus is about the well-being of human life. Every religion actually focuses that everything cooperates for the well-being of human life. Human life without science is unimaginable. Be it from past till today, whatever progress in the life of mankind has happened, the greatest role is of science. Without science, I hope the progression what today has happened would not have been possible. Though most of them don't know science exactly as it is, but through our daily lives, in one or the other way, science has been part of our life. So today's the cozy life, the comfortable life, the peaceful life, and even the happy life which human beings take is because of the great support that science and technology has been rendering to this humanity. First of all, I would thank all the people, those who are involved in different streams of science, in different forms of science, research work, experiments, and lecturing sessions, imparting their knowledge of science. I first of all thank all of them for this great service that they're doing for the humanity. Secondly, in such a crucial situation, everyone knows from past few months how the whole world is shook because of this pandemic, and how this process of learning and reading process has been simply struck, and everything at a moment was thought that it is the end, nothing is going to happen, how we are going to face. But one thing is sure, man cannot be stopped. This webinar in this crucial time has been a great help, as the participants were expressing, to enhance their learning and also to continue to what may come. Really, it's indeed a great thing that these online sessions and webinars which are going on. And I'm very happy that our institution also has not fallen back in this process. And I really, on the behalf of our management, congratulate and thank the physics department of PG and UG for organizing such a wonderful program for past 6 days. It's not simple, an international seminar lecture session being for 6 days, really it shows how much of work has gone behind and how much of effort you have taken. The management is very happy and the management congratulates both the departments, Professor Revan Siddhaya and Professor Shobna Thomas, and all the department people, those who are coordinated with this. Sincere thanks to all of you. And a special thanks for the speakers. Both of them have been with us all the 6 days and been gracious enough to share the rich knowledge through the platform of our institution. I extend heartfelt thanks to both the speakers for being part in our institution. I also thank the technical support given by our media journalism department for seeing that nothing goes off and everything goes on well. Thank you very much. I pray and wish that 3 days really would have been a um, uh, great venture to quest the knowledge of all those lovers of physics. And I'm sure all the participants would agree with me. I sincerely thank all the participants for being part of this and making this webinar a really successful one. Thank you, dear participants. May God bless you all. Have a wonderful day. May God give all of us good health. Thank you.
Thank you, Father, for your kind words of appreciation and constant support in all our endeavors. Dear participants, kindly note you can now find the link to provide your feedback in the Zoom chat box and YouTube comment section. Do fill the form and submit. It will be available for another 10 minutes. You will receive an e-certificate only upon submission of the feedback form. I now request Mr. Philan Amal, PG Department of Physics, St. Philomena's College, Mysore, to propose the vote of thanks.
A very pleasant afternoon to respected dignitaries and all our participants across India. It's my privilege to have been asked to propose the vote of thanks for the online lecture workshop on energy bands in solids and electrical transport properties of metals and semiconductors. First of all, I thank the Almighty for having brought us together for this purpose. I thank the college management for the constant support and encouragement in making this event a grand success. I express my heartfelt gratitude to Reverend Dr. Bernard Prakash Barnes, Rector, St. Philomena's Institutions, for his constant motivation. I'm very grateful to Reverend Father Maria Xavier for sharing with us his views and words of inspiration. I thank Dr. T. Ruth Shantakumari, Principal St. Philomena's College, in her absence, for her constant support. I must mention our deep sense of appreciation for Professor R. Srinivasan, the convener of the lecture workshop and resource person, for his excellent coverage on reciprocal lattice, energy bands, and density of states. He has been a guiding force and has supported us in all our endeavors. Thank you, sir. I thank Professor Othbert Pinto, Director, PG Studies and Research Center, St. Philomena's College, who in spite of his busy schedule made his presence here possible. Thank you, sir. I'm further grateful to Professor G. Umesh for his elaborative lectures on electrical conductivity in solids, band gap measurements in semiconductors, and mobility of charge carriers in semiconductors. It was a great joy listening to you, sir. On behalf of the organizing committee, I thank you, sir. Well, dear participants, an event like this cannot happen overnight. The wheel started rolling weeks ago. It requires planning and a bird's eye for every details. We have been fortunate enough to be backed by a team of very motivated and dedicated colleagues of UG and PG departments of physics under the guidance of Professor D. Revanasiddaya and Professor Shobana Thomas. I thank all the members of the organizing committee for their enormous cooperation in organization of this event. I thank the Science Academies of India for their generosity towards organizing and conducting this 6 days lecture workshop. I would like to take this opportunity to place on record my hearty thanks to Mr. Akin Sridhar, Mr. Arun George Matthew, and Dr. Venugopal for their perfect broadcasting support from the studio and their willingness to take on completion of tasks beyond their comfort zone. I thank all the participants for their active involvement throughout the lecture series, without whom this event wouldn't have been a success. Finally, I would like to express my sincere gratitude to every person who has been part of this 6 days lecture workshop. Thank you, one and all.
Thank you, sir. Herewith, we have formally concluded our 6-day online lecture workshop. Hope to see you all soon in our next international workshop on supernovas and neutrinos in the month of February 2021. Thank you, everyone. Have a good time.
The college started postgraduate courses in the year 2008 in chemistry and social work. After becoming autonomous, it added few more courses in all disciplines. Today, the college has 11 postgraduate programs under choice-based credit system pattern. The courses are designed to give weightage in core papers to learn more of skills, supported by soft core papers and open elective from other departments to enhance students' knowledge beyond their program. The University of Mysore has recognized the chemistry, social work, journalism, and physics departments as research centers. 4 students have enrolled for their PhD program. To provide better facilities, an independent postgraduate center was established with well-designed labs, library, classrooms, and multimedia projectors with internet connectivity and uninterrupted power backup. The overall program outcome of postgraduate courses is to train the students to acquire knowledge leading to innovations, entrepreneurship, new technologies backed by effective communication skills. The curriculum of the programs is regularly revised as per the need of the society. Some of the major innovations introduced in the curriculum are open electives, interdisciplinary papers, and Swayam MOOC courses. The students are trained through blended teaching with flipped classes. The students and faculty members continue to enrich their knowledge by organizing and attending seminars, workshops in the college. To inculcate research culture among the staff and students, the department have introduced project works leading to publication of original research articles in reputed journals. The college is also bringing out a biannual St. Philo's multidisciplinary peer-reviewed research journal with ISSN number to publish their research articles. The faculty members have completed UGC-funded research projects. The management also supports with seed money to carry out research.